How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at cubic structures of solids. So our objectives will be to explain the atomic structures of solids in terms of the various cubic unit cells, including simple cubic, sometimes called primitive cubic, as well as body-centered cubic and face-centered cubic. And then also apply trigonometry to determine the dimensions of a unit cell. So structures of solids. So a unit cell is the simplest repeating unit of a solid. So if I'm looking at a two-dimensional particle diagram of a solid, it may look like this neatly organized layer. 3 dimensions, there's another layer like this. Now a unit cell is the simplest repeating unit of that solid. So for this, that would be the simplest repeating unit. If I drew like 3 dimensions, it's going to look like this kind of cube. The corners of that unit cell we call lattice points. So the lattice points on this drawing would be like these are the lattice points. So this example is the simple cubic crystal lattice structure. And if we take a look, each lattice point has added 1/8 of an atom. So you can see this region right here represents 1/8 of an atom. And if I had a full atom, it was cut in half this way, it was cut in half this way, and it was cut in half another way. Do that, cut in half 3 times, you get 1/8. Now, since there are 8 lattice points on this unit cell, there's the equivalent of 1 full atom in each unit cell. Now, each side is the equivalent to 2 atomic radii. So you can see this would be the center of an atom. That would be the very outside. So that is 1 atomic radius. So the rest of it is another atomic radius. So each side is the equivalent to 2 atomic radii. This kind of cubic structure only fills up about 53% of the space. So there's a lot of empty space in this unit cell. So the coordination number is simply the number of other particles that a particle in a solid touches. So here I have an example that's like 3 deep. I don't know if you could see, but there's like a red particle circled in there. We're going to go, hey, how many particles is that one touching? Well, you can tell from the surface, there's only 1 other particle that's touching that one. So when I fade away all the particles it's not touching, you can see this one is touching 1, 2, 3, 4, 5, 6 other particles. So the coordination number for this cubic structure will be 6. So simple cubic structure has a coordination number of 6. Example problem, we got polonium-209 solid takes on a simple cubic structure and has a side length of 336 picometers. What is its atomic radius? Well, we know that, hey, from this corner to that corner, there are 2 atomic radii. And it also told us that that length is 336 picometers. If we want the atomic radius, we do 336 picometers divided by 2 because it's 2 radii, and that gives us 168 picometers. So that would be the atomic radius of polonium based on that data. Follow-up question, hey, same stuff, but what is its density in grams per cubic centimeter? They give us the atomic mass in grams already. They want grams per cubic centimeter. So we know that density is grams per volume. So let me do a little math. I know that in this unit cell, at each corner, there's 1/8 of an atom, and there are 8 corners. So that tells me that I have 1 full atom. So I have 3.47 times 10 to the minus 22 grams in 1 unit cell. So 3.47 times 10 to the minus 22 grams. Now for the volume, I know that each side is 336 picometers. But let me get this into centimeters so that I can do centimeters cubed. I know pico means 10 to the minus 12. So if I have 1 picometer, that is equivalent to 10 to the minus 12 meters. Now I can get it to centimeters. Well, if I had 1 centimeter, that tells me that it's 10 to the minus 2 meters. Meters cancel out, picometers cancel out. And when I do 10 to the minus 12 divided by 10 to the minus 2, it gives me 336 times 10 the minus 10, and I can leave it just like that. But the volume is going to be that number cubed. So I get 3.47 times 10 to the minus 22 divided by 336 times 10 to the minus 10 centimeters, and then that gets cubed. And when I plug and chug and get an answer for that, I get, what's it, 9.15 grams per cubic centimeter. So that's how you're going to do problems like that. All right, bodied centered cubic, or BCC for short. It's like a simple cubic cell, but with a whole atom stuck in the middle of it. So we start with, hey, here's the back. There's 4 atoms there. Stick a atom in the middle, and then surrounded by the front, another 4 atoms. In 3 dimensions, it's going to kind of look like this, right? We have our lattice points at the corners, and then we have a full atom in the center of that. So each lattice point has 1/8 of an atom. Got an additional atom in the center of that, which tells me that there are 2 atoms in each unit cell. Now the diagonal lattice, or I'm sorry, the diagonal lattice point. So this lattice point to that lattice point internally is going to be 4 atomic radii, right? We have 1 atomic radii there. I got 2 for that internal atom, and then a whole nother one for that one. We probably won't do a whole lot of math with like, what's the atomic radius if this is the unit cell side length, because it's going to be a little ugly, but you could just keep doing quadratic stuff. The coordination number for this is going to be 8, and hopefully you can see that relatively easy. If I'm looking at this center atom, how many atoms is it touching? Well, it's touching a total of 8, and that's going to be true for all the other atoms as well. This one fills roughly 68% of the space, so it's a more efficient packing of space than the simple cubic. Which brings us to face-centered cubic. Each face has an atom centered on it, so it looks like a 5 on the dice. So this is just one face, right? So we have an atom in the middle, and then we have 4 on the corners. It kind of looks like a 5 on a dice. So then each face, well, there's 4 other faces, so they each have one centered on them, and then there's also another one right there. So this is what it looks like in 3 dimensions. So you can see each corner still has that 1/8, but each face also has 1/2 of an atom in each unit cell. So let's do the math. If each face has half an atom, all right, each corner has 1/8, there's 8 corners, that gives me 1 atom. And then each of the 6 faces has half an atom. That tells me there's 3 atoms there, so I get a total of 4 atoms in each unit cell. The diagonal on any face, so from here to there, is 4 atomic radii. All right, this one, really efficient, relatively speaking, filling space. 74% of the space is filled with this cubic structure. This is also known as cubic closed packing. So if you see that, it's talking about the same thing. Coordination number gets a little difficult to show in a 2-dimensional thing. So picture this hexagonal arrangement of atoms as the base. And then we have another layer, identical, but staggered to fill in the gaps, and then a 3rd layer doing the same thing. Now, that atom that I circled in red is going to be our atom to focus on. How many atoms are touching it? Well, on this top layer, there's only these 3 that are touching it. So let me remove those. Now on this layer, well, there's 6 touching that one on that middle layer. And if I take a look at the layer below it, well, these 4 are not touching that atom at all. So if I move that to the side and I start counting, well, how many atoms are touching it? Well, there's, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this has a coordination number of 12. Sample problem, calcium crystallizes to take on a face-centered cubic structure with a side length of 559 picometers. What is the atomic radius of calcium? So we know that this is 559 picometers. And we know that from this corner to that corner, there's 4 atomic radii. We're trying to figure that out. That's where we're going to need the little, a squared plus b squared equals c squared math, where a squared and b squared are the same number, 559. So it's really 559 squared times 2, because we're adding them together, has to equal my c squared, which is my 4r squared. So now if I do the algebra, which I'm not too interested in showing you guys, I trust you can do it. When you do that math and you solve for r, you get 198 picometers. Right, so you can go, hey, let me square root both sides, and then divide by 4 to get rid of the 4. And when you do that, you get 198 picometers. Follow-up question, what is the density in grams per cubic centimeter? And they give you the mass of a calcium atom. So again, we got to go, hey, I have 1/8 at each corner. So that gives me 8 corners, 1 whole atom, plus I have 1/2 on each face. There's 6 faces, so 3. I have 4 atoms total. So again, if I want density, mass over volume, I know my mass is going to be 4 times, that's 6.66 times 10 to the negative 23 grams, divided by, all right, well, picometers, not my favorite thing, right? I need it in centimeters. So I do a little conversion. I know pico means 10 to the minus 12. So if I have 1 picometer, I have 10 to the minus 12 meters. Now let me convert that into centimeters. I know if I had 1 centimeter, that's 10 to the minus 2 meters. Meters cancel out, picometers cancel out. 10 to the minus 12 divided by 10 to the minus 2 gives me 559 times 10 to the minus 10 centimeters. Now my volume is going to be that number cubed, 559 times 10 to the minus 10 centimeters cubed. And when I plug in chug and I get my answer there, I end up with 1.53 grams per cubic centimeter. There you go. All right, summarize. Can you explain the atomic structure of solids in terms of the various cubic unit cells, meaning simple cubic, body-centered cubic, and face-centered cubic? And can you apply some trigonometry to determine the dimensions of a unit cell or atomic radius? Hope you found it helpful. See you in class. Okay, bye.